Hello students, welcome back to the course on Principles and Chemical Applications of Thermodynamics. Today we are going to cover a mathematical topic which gives you the foundation of thermodynamics. To explain where this mathematics comes in, let me remind you that we have already discussed this, that the equilibrium properties of a macroscopic system is quantified in terms of some states or equilibrium states. And for any given system, we require three macroscopic variables to define the equilibrium state of a macroscopic system. So in my last lecture, we talked about a system like this, where 1 mole of an ideal gas is contained within a stainless steel container, and this entire setup is then put in contact with a thermostat. Then, when the gas has established a thermal equilibrium with the thermostat, we define the equilibrium state of this system in terms of the temperature, volume of the gas, and the number of particles present in the gas. In an alternative situation, you would have a little more complicated setup where the stainless steel cylinder containing the gas molecules, it is still immersed in this thermostat, but one side of the cylinder is attached to a frictionless, wetless, movable piston, and we have put in a weight over here, and the pressure exerted by the weight on the gas can be measured using a barostat. If you allow the system to establish a thermal and mechanical equilibrium with the thermostat and the barostat, then how do you define the equilibrium state of the system? You define it by reading out the temperature of the system from the thermometer, the pressure of the gas from the barometer, and obviously I know how much gas we have put into the cylinder, so I know the number of particles present here. And therefore, it is very clear that what we are dealing with in thermodynamics is essentially a multivariate system. So any thermodynamic property of any of these systems will be dependent on the three variables which define its state. So that is the basic understanding in thermodynamics. Now, I have also mentioned that we are interested in a change in state and trapping of energy in the form of useful work done by the system on the surroundings when it is undergoing the change in state. And therefore, it is very important to understand how the measurable properties or the energies of the system are going to change in terms of system variables like T, V, and N. Why is that so? That is because when the system undergoes a change in state from an initial equilibrium state to a final equilibrium state, I know that the value of T, V, or N, all of them or one of them or maybe two of them will change depending on the kind of experiment you are carrying out in order to carry out the change in state. And therefore, the energy will also be changing as a function of these three variables. And this brings us to the concept of multivariate calculus. And here the important idea is I have two independent variables, for instance, like x and y. Let me have a function which is a function, dependent function of these two variables, f, which I represent as f of xy. Therefore, if there is a change of the value of the independent variables, the value of x initially was x1 and then it changes to x2, and then the value of, at the same time, the value of y was y1 and it changes to y2. The question is, since the value of f depends on the values of x and y, then obviously due to this change in values of x and y, there will be a corresponding change in the value of f as well. So what would be this new value of f? That will be the value of f estimated at the new point, that is x2 and y2, minus the value of f estimated at the old point where x was equal to x1 and y was equal to y1. Now, if this change is an infinitesimal one, then I would expect the value of x will change by an infinitesimal amount so that its new value becomes x plus dx. Similarly, I would change y to y plus dy. In that case, once again, I do expect f to change. And what would be the change in value of f? So f, which is a function of x and y, will now have a new value because in the new point x is equal to x plus dx and the new value of y is y plus dy. And therefore, the new value of f is f plus df. So what is df? df, once again, just like the equation that I have shown to you earlier, the value of f at the new values of x and y minus the value of f at the old values of x and y. Therefore, as you understand, as the system changes by changing the values of the independent variables x and y, there is a corresponding change in the value of the dependent variable f. Therefore, if I want to know how energy changes with the variation of thermodynamic state, I need to understand the variation of energy with respect to all the three variables on which the state of the system depends. And this brings us to the concept of dependence of one dependent variable on two or more independent variables. And this brings in the concept of partial differentiation. So here, let me consider once again a function of two variables. So by definition, I have two independent variables x and y and one dependent variable f. So typically, this is a very complicated function f of xy. So as you can see, for a given value of x and y, this is the corresponding value of f. For some other value of x and y, this is the corresponding value of f. Now we are asking the question, what is the partial derivative of f? That is defined as the rate of change of the function f with respect to one variable with all other variables kept fixed. So in this case, how many independent variables you have? We have two independent variables x and y. Therefore, if I want to know the rate of change of the function f with respect to x, I must be keeping the other independent variable y fixed and then find out the rate of change of f with respect to the independent variable x by keeping y constant. And in the limit delta x changing to 0, this is the definition of the partial derivative of f. In an exactly similar manner, one can define the rate of change of f with respect to the other independent variable y by keeping x constant. Now, you must have seen this definition of derivatives when you came across the simple derivatives while you take the differentiation of a function which depends only on a single variable. So what is the difference that I am introducing here? I am simply saying that yes, the same kind of definition is valid, but here we have more than one independent variables, and therefore the derivative of f that I take is not a total derivative with respect to one independent variable only, but now I am taking a partial differentiation of the function which depends on more than two independent variables. Now let me take one example over here. So this is a function of two variables x and y, and its analytical form is given by x square into y. So let us now work out what is del f del x keeping y constant. So basically what I will have to do is I will keep the y constant and then do del x of the rest of the function. Rest of the function is actually nothing but a function of x. So the result would be y into 2x. So please try to understand that this portion is a simple differentiation. Similarly, I can try and find out what is del f del y x. So clearly, while taking this differentiation, I'll have to keep the x dependent part out of the differentiation, and then I take differentiation of the y dependent part. So what is del y of y? That is equal to 1. So this answer is x square. So as you see that by knowing the rules of simple differentiation, one can find out the partial differentiation of a function of two derivatives. So basically then this is a set of results that we have got in this slide. Now the next property that I would like to highlight is the first order differential of f of xy. So here df is the first order differential of f when f depends on two independent variables x and y. So obviously you understand that if x undergoes an infinitesimal change by an amount dx and y undergoes an infinitesimal change by dy, then df depends on dx and dy. And this simple expression tells you that there is a coefficient with in front of dx and there is another coefficient in front of dy, and these are nothing but the partial differentiation of the function with respect to the corresponding independent variable, keeping the other independent variable fixed, as you see from here. So what does this expression say? This expression says that this is going to be the net first order differential change in the function f when both x and y are simultaneously undergoing an infinitesimal change to x plus dx and y plus dy respectively. There is the second definition that I have highlighted in this slide, and that is the second order partial derivative of f of xy. So basically here what you are saying is, let me say that for function f you have already evaluated this partial derivative where you have taken a derivative of f with respect to y keeping x constant. Now when you keep x constant, then you get some function that is another function g of xy, and I am asking you to take another derivative of g of xy with respect to x now, keeping y constant. Therefore, if I use the full notation, I would say that this is del del x of g of xy keeping y constant, and this would be equal to del square f del x del y, and this is the second order partial derivative of the function f of xy. Once again, this second order partial derivative could also have been taken by taking this derivative first, which let me call it as h, and then the final answer would be del h del y keeping x constant, and that would be equal to del square f del y del x. So as you see in the second order partial derivative of fxy, the way you take the derivative, the order in which you have taken the derivative is appearing in the denominator here. I'm not going to go into the details of the validity of these derivatives and whether this second partial derivative is equal to this second order partial derivative. In general, for all the cases that we are interested in while studying thermodynamics, it doesn't depend in which order you take the two partial derivatives. The results usually are the same. So this in general for most of the thermodynamic functions is equal to this second order partial derivative. So once again, let us work out a few examples. So what do you think is going to be df? As you see, we know that df is equal to del f del x y dx plus del f del y x into dy. Now what is del f del x? That is 2xy, and I can put it in. So the first term will now be written as 2xy into dx plus what is del f del yx? That is here. So this is going to be x square into dy. Now the next question is, how do I find out this second order partial derivative? Okay, here I will first find out what is del f del y is with keeping x constant, del f del y x, that is equal to x square. So if I want to find out this derivative, then I'll have to take a del del x of this quantity by keeping y constant. Is that clear? So if I take a derivative, then this quantity now becomes del del x of this function of x and y keeping y constant, and that turns out to be 2x. Right? Similarly, you can do the other second order partial derivative as well and see that the results are the same independent of whether you are writing del square f del x del y or del square f del y del x. If I move forward, then as you see that the results have been summarized over here, you can check these results yourselves. Now in the next part, I'm going to highlight what is known as the chain rule. For this purpose, let me introduce to you S to be an independent parameter such that x is a function of this parameter s, y is a function of this parameter s, and since f depends on x and y, therefore fxy is also a function of s. In that case, I can say that if I change the value of s, the value of x will change, the value of y will also change, and correspondingly there will be a change in the value of f. So now I am asking, what is df ds? Please note that since f is a function of s directly, therefore this is an ordinary differentiation and not a partial differentiation. Now df ds, just because I know that df is equal to del f del x, keeping y constant, to dx, plus del f del y, keeping x constant, into dy, I am now taking derivative of both sides with respect to s. So the result is df ds, keeping this constant, into dx ds, plus del f del y into dy ds. So this is how the chain rule works. Now there is something called a cyclic rule. And what is that? Let us say that I have a function z which is a function of x and y. So this mathematically means that there is a functional relationship between the three variables x, y and z. If that is so, and if I can define the partial derivatives that are shown over here, in that case I can always write that del y del z, keeping the third variable constant, and all possible such combinations such that all of them come once in the numerator and come once in the denominator, the result is going to be -1. So these two rules are relationships that we use very frequently in thermodynamics. There is one further concept that I am going to explain to you here, and that is the concept of an exact differential. So what is an exact differential? For a total differential of f of xy, we have seen that I can write it in this form, where df is something into dx and something else into dy. These coefficients which appear with dx and dy respectively, these are general functions of x and y. And by definition, what is m? M must be the partial derivative of f with respect to x, keeping y constant, and n is the partial derivative of f with respect to y, keeping x constant. Then the question that we are asking is, would any expression that can be written in this form always represent the total differential of a function? The answer is, from differential calculus, we have learnt that this happens if and only if the partial derivative of m with respect to y, keeping x constant, which is this quantity, if that becomes equal to the partial derivative of n with respect to x by keeping y constant. So then I would say that if this condition is met, then df, which is given by mxy dx plus n dy, that is an exact differential. So now let me take one example and check if this is an exact differential. So here, can you identify in this expression what is m? Of course, this is m and this is n. So my point is, I need to find out del m del y. So del m del y keeping x constant, that is equal to 2x into y keeping x constant, so the answer is 2y. Similarly, I can find out del n del x keeping y constant. The answer in that case will be that all these partial derivatives, so what is del n del x keeping y constant? Del n del x keeping y constant, sorry, this is 2x and this is also 2x. So I understand that this derivative is equal to this derivative, and therefore this expression is an exact differential. Actually, by inspection, you can say that here I have this expression is equal to d of this function, x square y. Similarly, there is another example that I have shown to you here, and you can very easily show that this expression is nothing but this is equal to df, where f is equal to x cube into y square. So what have we learned from here? We have learned that in thermodynamics, there are more than one independent variables. To be precise, there are 3 independent variables defining the equilibrium state of a system. Therefore, if I need to understand how the energy of the system is changing with a change in state, I need to understand how energy is changing with the variation of 1, 2 or all the 3 variables. And therefore, ordinary differential calculus is not going to be sufficient to have a mathematical formulation of thermodynamics. And that is the reason why we looked at how to use partial differentiation when I have a function dependent on 2 independent variables. We shall next look at what inexact differentials are, now that we have learnt what exact differentials are. Thank you.